Imagine the most refined turbofan ever engineered. A masterpiece of aerodynamic optimization, one that cannot be brought online. At least, not at the temperatures required to achieve the goal. The dominant narrative claims, more heat equals higher efficiency, pure thermodynamics. But inside the design room, there is an invisible wall, the turbine inlet temperature limit. The failure is not a cinematic explosion. It is creep, oxidation, and thermal fatigue, as the metal slowly yields under sustained heat and stress. 1,600 degrees Celsius. That is the engine's breath, the turbine inlet temperature. The metal designed to sustain it has a melting point near 1,400 degrees Celsius. We are flying within a paradox, a machine operating continuously in an environment that, by all material limits, should reduce it to liquid. Nickel-based superalloys enter the scene, atomic-level elite soldiers, engineered to survive where ordinary metals fail. But they have an enemy, creep, time-dependent deformation under extreme temperature and stress. Under brutal centrifugal loads, the metal begins to stretch, slowly, relentlessly. If a turbine blade grows by even a single millimeter, tip clearance vanishes, and the game is over. To avoid melting, we bleed the engine. High-pressure air is diverted from the compressor and routed into the turbine, where it becomes a thin thermal shield, film cooling between metal and flame. But remember, every kilogram of air used for cooling is a kilogram that does not pass through the core to produce thrust. It reduces mass flow, alters pressure ratios, and steals efficiency from the cycle. In a jet engine, efficiency is not a free gain. It is a battlefield of trade-offs, where every degree of cooling is paid for in performance. Up to this point, we have been stealing air from the engine to protect the metal. But there is a limit to cooling alone. At some point, air is no longer enough. What we need is a barrier. That is where asterisk thermal barrier coatings, TBCs, asterisk enter the picture. TBCs are ultra-thin ceramic layers applied directly onto turbine blades. They produce no thrust. They do not move, but they fundamentally change the thermal balance inside the engine. TBCs act as a passive thermal shield. They dramatically reduce the heat flux reaching the metal substrate, lowering the metal temperature by hundreds of degrees, even as the surrounding gas temperature continues to rise. While the flame gets hotter, the metal stays below its melting limit. This is not simple insulation. These ceramics are intentionally porous, engineered at the microstructural level to slow heat conduction, resist oxidation, and survive extreme thermal gradients. Without them, the environment inside the turbine would be completely unsustainable. By reducing the thermal load on the blade, TBCs also reduce the amount of cooling air required. And every kilogram of air we no longer divert for cooling is a kilogram returned to the core, producing thrust. That is how efficiency is reclaimed, without crossing the line into melting. Up to this preventing point, the ceramic coating has done its job. The fire is still there, but the metal survives. The problem is that a jet engine does not live at steady state. Every start, every throttle change, every shutdown, metal and ceramic expand differently, at different rates, with different coefficients. And inside that microscopic mismatch, a silent enemy is born, spallation. The thermal coating does not melt. It cracks. It debonds. It flakes away in invisible fragments, not because of peak temperature, but because of repeated thermal cycles. Once the ceramic layer is lost, the metal is exposed, and the thermal margin disappears in seconds. That is why, in a jet engine, even the best protection has a finite life. We do not fly until something fails. We fly until the clock says stop. And once the coating spalls, the clock starts ticking. No matter how advanced the superalloy is, no matter how sophisticated the cooling system becomes, every hot section component in a jet engine has a finite life. This is where life limits come in. Every turbine blade is born with an invisible counter etched into its crystal structure. Each thermal cycle, startup, takeoff power, shutdown, leaves a microscopic scar. Low cycle fatigue, cumulative damage, micro cracks you can't see until they grow. Engineers don't wait for failure. They rely on damage models, accelerated testing, and conservative margins to define the exact moment a blade must be removed. Not because it has failed, but because it might. In aviation, you don't design for failure. You design to remove the part before failure ever happens. Because a single blade exceeding its life limit doesn't just threaten the engine, it threatens the entire aircraft. This isn't about heroics. It's about discipline, prediction, and absolute control over time. As the clock approaches its limit, chance is no longer in control. Maintenance is. Before a crack grows, before a blade exceeds its certified life, before failure has a chance to happen. This is where inspections come in. some visible, others invisible to the human eye. Non-destructive testing. Ultrasound to listen inside the metal, eddy currents to reveal surface cracks, X-rays to expose what the fire tries to hide. Each technique pursues the same goal: detect damage before it becomes critical. And then there is the borescope, a camera that enters the heart of the engine without disassembly. It scans blades, coatings, and leading edges, looking for cracks, TBC spallation, early signs of creep or fatigue. Maintenance doesn't fix failure. It prevents it. Because in aviation, safety doesn't rely on making things indestructible. It relies on knowing exactly when to stop using them. After inspections, clocks, and maintenance, one truth becomes unavoidable: an engine can be perfect on paper. The Brayton cycle is elegant. Higher turbine inlet temperature means higher thermal efficiency. More useful work extracted from the same airflow. The equations are correct. But the cycle doesn't fly. Materials do. Every calculation carries an implicit assumption that the metal can survive the temperature the theory demands. And that is where thermodynamics hands control over to materials engineering. Efficiency is not limited by air or compressors or combustion chemistry. It is limited by what happens at the atomic level inside a blade spinning thousands of times per second, surrounded by fire. That's why every gain in efficiency doesn't begin with a new equation. It begins with a new microstructure, a new alloy, a new coating. Brayton defines the target. Materials define how far we can go. If the Brayton cycle defines the theoretical ceiling, materials decide whether that ceiling is glass or steel. This is where CMC's ceramic matrix composites enter the story. Not as marketing hype, but as laboratory data, test cell hours, and real engines running at the edge. Companies like GE Aerospace have demonstrated through published lab tests and operational engines that CMCs can operate hundreds of degrees hotter than nickel superalloys without melting, without metallic creep, and at a fraction of the weight. Less cooling air, higher turbine inlet temperature, real efficiency gains. Pratt & Whitney and Rolls-Royce report similar results from high-temperature rigs and extreme thermal cycling. CMCs don't win by brute strength. They win by changing the rules of the game. But this is not a fairy tale ending. Brittleness, impact resistance, cost, manufacturing, and certification are the new battlefield. And that's where the real story begins. In the next video, we'll go deep. What CMCs really are, how they're made, why they survive where metals fail, and what still prevents them from dominating every turbine stage. If you want to understand the thermal future of jet engines, subscribe and turn on notifications. This is just taking off.